Hello, in this video, we're only gonna talk about how do we convert numbers to a rational number. So sometimes the question could be that can you show that a certain number is rational? Okay, something like show that maybe 0.1 with a dot is rational. Okay, we normally use what we call the recurring fractions so that we can move them from this kind of a format to something like A over C. That's what the question simply wants you to do. Okay, so in this case, we're just gonna go over step by step. So let's say we have this 0.1 recurring. Okay, let me just write it this side. So we're saying 0.1, we are saying express 0.1 recurring as a rational number. Okay, as a rational number. Okay, so what we're going to do, I always prefer asking my learners to start by letting the given expression be equal to a certain letter y. There are quicker ways, but in most cases, we want you to show how you obtain your answers. So I'll say maybe let y be equal to this whole thing, 0.1. Remember, recurring simply means we're just writing the same thing and so on and so forth. So I'm just using 3 numbers just for convenience. Then the question is going to be, how many digits will this comma move? Or how many places will this comma move to cover the numbers that are recurring? So it's just one number that is recurring, which is a 1 across. So what we're going to do is we're basically going to multiply by 10 on either side. Okay, if this is our equation number 1. So 10 on the left is going to be 10y. 10 on the right is going to be 1 comma. We need to keep the same number of decimals. Okay, because the 1 continues, never ends. Okay, this is equation number 2. Then we're going to get equation number 2. We subtract equation number 1. So 10y minus 1y, we get 9y. And then 1 comma 111 minus 0 comma 111, we only get a 1. Then divide both sides by 9. That's going to be 1 over 9. So we've expressed the number just as a fraction. All right, so let's see with these examples that we have. Okay, so they want us to convert 0.45. So we can see the dots on 4, can see the dot on the 5. So which means 45 is recurring. Okay, so let's see. It's telling us 0.45 recurring, which means this sum or this number could be 0.45, 45, 45, and so on. So step number 1, we let any letter, let's use maybe M, be equal to 0.45, 45, and so on and so forth. Let's call that equation number 1. Then, how many digits must the comma move, or how many places must the comma move to cover the numbers that are recurring? So we are seeing that 45 is recurring. So the comma must have 2 spaces or must cover 2 digits. So for 2 digits, we're going to multiply by 100 because every step that the comma moves is just a multiple of 10. So I'm going to say 10 on the left, 100 on the left, which is 100m, and then 100 on the right, which is going to be 45, 45, and then 45. This becomes my equation number 2. Then from there, all I need to do is just to subtract the second equation and the first one. Okay, so I'm going to say equation number 2 minus equation number 1. So 100 minus 1, that's going to be 99m. And then 45 minus 0 is just going to be 45. These ones will just cancel out for as long as you've kept the same number of decimals or the same number of digits after the comma. Then from there, just divide both sides by 99. So, which means our m is going to be 45 over 99. And then all you have to do from there, we see that there's something common between 45 and 99. So you can go ahead and then reduce that. Can we use 9? Is it possible for us to use 9? Yes, it's possible. Because we know that 45 divided by 9 is going to be a 5. and then 11, sorry, 99 divided by 9 is going to be 11. So this becomes our final answer. So we've expressed that as a rational number. All right, then we have this 1.2, where we have 0.15. It's only the 5 that is recurring. Let's see how we work out this. So 0.15, 5, okay, 15, and the 5 is recurring. So in other words, this is going to be, let me remove those dots, 1, 5, 5, 5, and so on and so forth. This is the question. So I'll use a K for now, be 0.155. I can say 5 as well. I'll call this equation number 1. Then there's a number that is not recurring, or there's a digit that's not recurring, which is 1. So I need to cover this digit, and it's only one number. So for me to cover it, I'll multiply both sides by 10. So this is going to be a 10K is equal to 1, triple of, I can keep it as a 555. Let me keep it that way. I'll call this equation number 2. Then from there, when I look at the first equation, alternatively, I can look at how many digits are recurring. It's just the 5, which is also 1 digit. So for me to cover the 1 digit, I can multiply this second equation by 10 again so that the comma can cover it. Or I can multiply the original equation by 100 so that it is covered. Okay, so when I multiply the second one by 10 on either side, I'll have 100K is equal to 15, I'll maintain the 3 5s. Now I'm having 3 equations here. Then my focus has to be equation 3 minus equation 1. So 100 minus 10, that will give us a 90K. And then 15 minus 1, that's going to be a 14. The 555s will cancel. Then I'll divide both sides by 90, then over 90. That cancels that. We can see that by 2 we have a 7, by 2 we have a 45. So my fraction becomes 7 over 45, okay? So guys, you can try to punch this in the calculator and you should be able to get just the same answer of 0.15 recurring. So there are, like I said, there are easier ways than quick. Okay, but if a question like this comes, it is 3 marks. So examiners usually want to feel, they want to see the steps on how you arrived at the answer so that you get all the 3 marks in that sort of manner. But nevertheless, the shorter ways, you still get all your marks. Okay, let's look at question 2. We have 2 numbers, okay? There's a pi, and then there's a 3.142. Telling us these 3 numbers are recurring. Okay. Can we classify the respective numbers as real and non-real? So in that video of the different types of numbers, we did discuss this and we said pi usually falls under what we call the real numbers. Same applies to this. This is also real. A number can only be non-real if we have a negative sign within the root, something like that. So both numbers are real, we do agree. Then 2.2, can we identify which number is further to the right on the number line? Which number is further to the right? So in other words, if we were to draw our number line, what is pi in normal sense? So if you have your calculator and you attempt to just punch this pi into the calculator, you find that it's 3.1, okay, 4, 1, 5, 9, 2, and so on and so forth. Then this one is 3.142. So between the two, which one is farthest to the right? So since this one is rounded off already, it's going to be farthest to the right. this one is extending because they all start with a 3 and a 3, then a 1, and then a 1, then a 4, and then a 4. And then from there, we have a 1, we have a 2. So that breaks it. Okay, so that 1 and the 2 will be the deal breaker. So which number is farthest to the right is going to be 3,142 recurring. Okay, then write down the rational number. So we say the rational number is one that can be expressed as a fraction. Examples will be those recurring. Anything that is recurring automatically becomes a rational. So it's going to be 3,142 recurring. And then lastly, can we prove that the number chosen in 2.3 is actually rational? So in other words, are we in position to write this number as a fraction? So step number 1, remember what we said? We let's use P equal to 3,142,142 because those are the numbers that are recurring. Then we can see that we can multiply by 1,000 since it is 3 digits, okay? So that's going to be 1,000p is equal to 3,142,142. Maintain the number of digits after the comma. Okay, then we subtract. If that is equation 1, that is equation 2, we do the subtraction. So 1,000 minus 1, I'm going to have the 999p is equal to, we have 3,142. We are subtracting a 3. We end up with 3,139. And then what we do is divide both sides by 999. So over 999 and then over 999. So this cancels that. And then my P becomes, say 3,139 over 999. I think I cannot simplify that further, so I'll just leave it like this. When you punch that in the calculator, you should be able to get that 3,142,142, and so on and so forth. So guys, that is how we express numbers as rational. That's how we convert fractions that are recurring into common fractions.